everyone. We'll start with the solving of May 2023 of Unit 2. Obviously, A is physics. So let's start. I'll just use the different ink. Sorry. Okay, yes. Okay, then we'll start with the solving of May 2023 Unit 2. We'll obviously solve starting with Section A, the first 10 MCQs, and then move on to Section B, the theoretical questions of this paper. So, question one says that waves may pass out as they, waves may spread out as they pass an object. Which of the following is the name of this process? So, whenever waves pass through an object, also that is also considered as a gap in that situation. So, obviously, when waves pass it through a gap, only diffraction occurs, right? So, obviously, option A is the correct answer now. For part two, the time period of a wave decreases. Which of the following properties of the wave increases? Okay, for time period, it is obviously related to frequency. As we can see, they are inversely proportional. So if time period has to decrease, then frequency need to increase. So for in this situation, the answer would be frequency, right? The time period is never connected to amplitude or speed or wavelength. Well, yeah, it is connected to speed also, but kind of in an indirected way, right? At first, they are connected to frequency first, so that's why we're going to choose frequency over here. Okay, then we'll move on. Question 3, the monochromatic. I hope by this time you already know why this example is using monochromatic. Because if it was not using monochromatic, then due to change in medium, if it was maybe using white light, which is a combination of 7 different colors, right? So in that case, when white light, combination of 7 different colors, passes through a change in medium, goes through this change in medium, they would disperse, they would not refract in that case. So that's why they're using monochromatic light. Not quite related to this question, but it is a good knowledge to have for these kind of concepts. Okay, so we'll start that monochromatic light is incident to a rectangular glass block. Some of the light is reflected and some of the light is refracted as shown. Which of the following properties does not change when the light is refracted? So whenever the light is refracted, the speed changes, the wavelength changes, but never the frequency. Okay, so option A over here would be the correct answer. But obviously take side notes for this, that whenever light passes from low dense medium to high dense medium, its speed decreases. Whenever light passes from low dense medium to high dense medium, its wavelength also decreases. So let's write from low to high, lambda decreases, and so does your value for frequency, value for your wavelength. But F always will be constant. Okay, so we're done with question 3. Moving on to question 4. The current in a the current in a uniform length of wire is constant. Which of the following graphs shows how the potential difference across the wire varies with the length of wire? Okay, so what exactly happens is that for a longer length of wire, electrons, when they need to travel a higher distance, right? The temperature increases, and due to this increase in temperature, their resistance increases. Okay, that is the usual case. So I'll just write it down. Whenever length increases, right, these leads on to your how would I express? Electrons need to travel a longer distance, so temperature decreases, therefore indirectly decreasing their resistance. So just write that electron travels longer distance, right? This causes the temperature to increase. So right, temperature to increase, this causes their resistance along the wire to increase. If the resistance along the wire is increasing, in that case, according to your equation, V is equals to IR, current is obviously staying constant. If R increases, obviously V also increases, right? So indirectly, if there is an increase in length, the voltage will increase, right? And that is the same case if the length decreases also. So for this part, if you go on to option A over here, it says that length is constant, but potential difference automatically increases. This really doesn't make any sense. So option A will certainly not be the correct answer. Option B, it says that length and like potential difference are kind of inversely proportional because an increase in length causes the potential difference to decrease. So this is also not the case. In this situation, it says that they are directly proportional but not like constant, or not exactly yeah, they do not have a constant directly proportional relationship. That is also not the case. They actually they have a constant directly proportional relationship. If your length increases by 2 units, in that case your potential difference also need to increase by 2 units. So option C is the correct answer, right? So yeah, this is it for question. Moving on to question 5, an electron has a de Broglie wavelength of 1.55 into 10 to the power of negative 9 meter. Which of the following gives the speed in meters per second of this electron? Now, for de Broglie wavelength, it's not exactly related to your speed, but it is somehow related to momentum, and again, momentum is related to speed, right? So over here, they have already given you the value for your lambda. So the original equation is lambda is equals to Planck's constant over momentum, where you can further break down momentum into terms of, sorry, I made a mistake. Momentum is p, right? Small p. Okay, so momentum is further broken down into mass into velocity. So if you make velocity the subject, you just change the position of velocity with lambda. So you get Planck's constant mass lambda. Right, now just input the values. The value for your Planck's constant is 6.63 10 to the power minus 34 over mass of your electron is 9.11 10 to the power of negative 31, and this should be further multiplied with your this value of lambda that is provided in your question, which is 1.55 multiplied with 10 to the power of negative 9. If you match this, then this is exactly your option D. So option D is the correct answer in that case. So we'll move on to question 6. Two waves of wavelength 12 have leave a source in phase, and the wave travels along different paths to a point X. The path difference at point X is 18 centimeters. Which of the following is the phase difference between the two waves at X? Okay, so now over here, whenever they try to find out this type of equations, then you have to find out the phase difference and only the wavelength between those two waves are provided. You never get confused about writing two waves in this kind of situations. Okay, you first find out the path difference between these positions. For example, when they meet at point X, the value was 18 and the value for your one complete wavelength was 12. So let's find out path difference. That is 18 minus 12, which is 6 meters, right? So now you draw one diagram for your one complete wave. Remember, for your one complete wave, the wavelength was actually 12 centimeters, right? And you can see from your calculation, you got your value for your path difference to be 6 centimeters. So if I draw one complete wave, this is the overall diagram for one complete wave. If this is 12 centimeters, then this part over here is 6 centimeters. And again, for 12 centimeters, the angle was 2 pi, as 6 centimeters is half of the 12 centimeter. So over here, the phase difference should be of pi. In that case, option C is the correct answer. Right, so you should always draw a diagram like this. At first, obviously find out the path difference, and then regarding that path difference or using that path difference, you draw a diagram and you find that position or that wavelength, right? Like at what position the path difference is situated, and according to that you find that angle difference. This was it. So we'll move on to question 7. Two waves are coherent. Which of the following must be true for the two waves? Okay. For coherent waves, for example, if I draw two waves, this is one wave and this is one wave, right? If they travel, if they are like actually produced from one single source, in that case, these two waves can also be incoherent. These two waves are in phase at some positions, might be in antiphase in some position. They might or might not have the same amplitude, but they like for two waves, for always to be in coherent, their frequency should always be same, right? All the other quantities might not vary, might vary, but frequency should never vary. For two waves to be coherent with each other, their frequencies must be same. So in that case, option D is the correct answer. Moving on to question 8. Light from a laser incident on a diffraction grating, causing a series of maxima to be seen on the screen. The positions of the central maxima and the first order maxima are shown. Which of the following changes would decrease the distance between the central maxima and the distance at the first order maxima, which is basically this distance, right? Which of the following would changes? Which of the following would change? Which of the following changes would decrease the distance between the central maxima and the first order maxima? Okay, so for this situation, for this x to decrease, the distance between the first order and central maxima to decrease, the first thing that is related to this is tan theta. I'll consider the distance between the diffraction grating and your screen is capital D, okay? So there's obviously an angle theta over here, we all know. So the first equation that follows this pattern, this situation is tan theta x over D. Right. Now, in this situation, for x to decrease over here, either case, your theta might decrease, or yeah, your theta or d both might decrease. Right. If I just take x as a subject, in that case, tan theta multiplied with d. So your distance between the between the screen and the diffraction grating, should it decrease, or your angle should decrease? Now, if I go to this part, the decreasing, the first option says that decreasing the distance from the laser to the diffraction grating. That means they are talking about this distance. This distance really doesn't matter and doesn't affect your distance between the first maxima and central maxima. So option A cannot be the possible answer. Increasing the distance from the diffraction grating to the screen, they're talking about this, right? Which is obviously related to your distance between first order and central, but they are talking about increasing the value for your capital D. That would cause an increase in your value for x, right? Because they are directly proportional. Capital D and x are directly proportional, which means that if you are increasing the value for capital D, x would also increase. But we are talking about decrease. So obviously, option B would not also be the possible answer. For C, they are saying that using a diffraction grating with more lines per millimeter, if they are increasing the diffraction grating for more lines per millimeter, then we can you have to consider the other equation, which is n lambda is equals to d sine theta. If you just make sine theta the subject, because over here theta is the only kind of what is it, theta is the only quantity that is related to your x over here. So if you just make theta the subject, in that case nd, this is the case, right? So if this is the case, if they are talking about that having more lines per millimeter, that means you're trying to increase the value for your small d. Small d represents the line, the distance between each line on those diffraction grating screen, right? So if you're increasing more lines, like now your diffraction grating has more lines, in that case your value for d is actually going to decrease, right? If you have more lines, that means the distance is supposed to be decreased for each line. So the value for D actually decreases. And if D decreases, as you can see, theta and D over here are inversely proportional. So I'll just write theta is inversely proportional to D. If D decreases, theta would increase. Indirectly, if theta is also directly proportional to X. So if theta increases, your value for X would also increase. So in that case also, you'll not get any decrease in value for your X. So this is also not the possible answer. The last one over here says that use light with a smaller wavelength. Okay, as we can see that yes, theta and wavelength are directly proportional. Right, theta is directly proportional to wavelength. So using smaller wavelength causes smaller theta. If you have smaller theta, in that case, you'll also have smaller x, which was the distance between your first and central maxima. So yes, option D is the correct answer. This question was quite like twisted, not tricky but twisted, because it was related with so many quantities for just 1 mark. Not kind of worth it, to be honest. We'll move on to the next question. Earth and Jupiter orbit the Sun as shown. The distance from Earth to the Sun is this, and the distance from Jupiter to the Sun is this. The intensity of the sunlight at Jupiter is Ij. Which of the following can be used to calculate the intensity of the sunlight at Earth? Okay, so you have to find out the intensity of the sunlight at Earth. Um, they are using some kind of equations. Okay, they are using the equation power, like power is equals to current intensity multiplied with area. Over here they actually cover up a spherical area which is 4 pi r square, right? So you can consider taking the equation like this, that the intensity of the sunlight to Jupiter is Ij. Which of the following can be used to calculate the intensity of the sunlight at Earth? Now over here the concept is that as the main sole provider of light is Sun, Sun's power will be same for both Earth and Jupiter, right? So we can write that P Earth is equals to Pj, power of Jupiter, and power can be further broken down to intensity of Earth multiplied with area equals to intensity of Jupiter multiplied with area, where you can finally write intensity of Earth, that is equals to intensity of J multiplied with 4 pi radius of your what is it, radius of your Jupiter, right? Yeah, radius of your Jupiter was 7.78 10 to the power 11. Everything divided by 4 pi 1.49 multiplied with 10 to the power of 11, right? As you can see, the 4 pi's will cancel with each other, and you're finally left with Ij multiplied with 7.78 10 to the power 11 square, right? So this is how you're supposed to get your answer as. And as you can see, this is your answer for option A. So we'll choose option A as your correct answer. Yes, yeah, with this, your question 9 ends. We'll move on to question 10. As the temperature of the filament in a bulb decreases, the resistance of the filament increases. Always remember that filament is a positive temperature coefficient conductor. I'll just write conductor over here. So for this, whenever the temperature increases, it is the decrease in the lattice vibration which causes the increase in the resistance, right? So which means that option A is the correct answer. If it was a negative temperature coefficient conductor, in that case, that would be the decrease in the number of electron conductors, right? In that situation, this is actually for the negative temperature coefficient conductors, which are like thermistors, right? Whenever the temperature of a thermistor drops down, your I'm wrong. Whenever the temperature of your resistance like thermistor increases, in that case resistance drop down because of this case. So this was the situation for negative temperature coefficient conductor, mostly known as your thermistors. So yeah, with this your entire section A ends. I hope it was clear for everyone. We'll move on to question 11 and also the start of your section B. Part of an electrical circuit is shown over here. In 60 seconds, this much electrons passes through point Z. Show that the current at Z is about 1.3. Okay, so we are assuming that current is flowing from this direction. Sorry, we are assuming current is flowing from this direction, because if it was flowing from the other direction, then the resistance would vary the entire current. So it first passes through point Z and then it enters your fixed resistor. So over here, you have 4.8 into 10 to the power 20 electrons, which means you have to find out the charge from this electron, right? If the charge for one electron is 1.6 into 10 to the power of negative 19, use unitary method to find the charge of this much 4.8 into 10 to the power of 20 electrons, right? And then again, if you have the charge, you divide the charge over 60 to find out your value for current. So I'll just do this maths in one go. That is I is equals to Q over T. Q is 4.8 10 to the power 20 multiplied with 1.6 10 to the power of negative 19 over 60, right? So if you calculate this, you can calculate, you get your value as 1.28 amps, which is almost close to 1.3. So that is correct, right? So value for your I is 1.28 amps. Now in 60 seconds, the resistor transfers 24 joules of energy. Calculate the potential difference across the resistor. Okay, so we also need to find out the potential difference, and they've provided you with energy. So we can start writing the equation like, you have to equate the two equations of power. The first equation of power is P is equals to IV, and the second equation of power is P is equals to energy over time. Right now again, time is provided and all. So if you substitute equation 1 into 2, the entire situation looks like this. IV is equals to energy over time. My writing for energy is wrong. In physics, you cannot write it like this because that one represents Young modulus also, right? So if you just make V the subject, you finally end up with energy multiplied with, sorry, not multiplied with, this would actually get divided with I and T, right? So if you take energy, that was 24 joules divided by I was 1.28 and current was 60. So if you calculate it, you finally get your voltage as 0.31 volt. And so this is the value for your voltage that will be provided to this circuit in order for that current to flow within this 60 seconds. I hope question 11 was clear to everyone. We'll move on to question 12. A student investigated the internal resistance of a cell using the circuit shown. As you can see, you have a voltmeter connected across that power supply and a variable resistor, and this entire circuit connected to this ammeter. The student used the variable resistor to vary the reading on the ammeter. He recorded corresponding readings on the voltmeter. The student plotted the results on the graph as shown. So the student plotted the results on the graph as shown. So the voltmeter reading and ammeter reading are plotted. As you can see, the graph is a downsloping graph. And for this kind of situation, what I always remember that this is the concept related to your internal resistance, right? Where you have this imaginary resistors with small r. This is the capital R, right? In that case, the equation that you are supposed to get, that was for EMF is equals to V plus IR. If you just like rearrange this, you can get this equation as minus RI plus EMF, which is exactly in the form of Y is equals to mx plus c, where m represents the gradient, which is equivalent to minus r, and your y-intercept represents your total EMF of the circuit, like the total power supply, like the total voltage of your power supply. Okay, so we'll move on to the next question. Determine the EMF of the cell and the internal resistance of the R. That we already explained in this part, but we have to just find out the gradient of this graph and the y-intercept. They never say that how would you calculate, explain your procedure. They just want you to find the values. Whatever process you use doesn't matter to them. They just want the working and the values for this EMF and the value for your y-intercept, internal resistance, right? So in that case, as your EMF was a y-intercept and this graph actually never meets your y-intercept, so you have to extrapolate this line until it actually meets the y-axis. In that way, you just take a straight line and do it like this. Wait, right, it's quite better. So what exactly happens from 1.4 and 1.6 over here? Between these five lines, you have 0.2 differences. You can write 1.6 minus 1.4 divided by 5. So over here, every line is represented with what, 4 units, 0.4 units. So sorry, 0.04 units. So that is, if I use a pointer, if this is what, 1.4, this will be 1.44. This is 1.48. This is 1.52. This is 1.56, and this is 1.6, right? So your line actually passes from in between 1.48 and 1.52, which is approximately 1.5 or 1.51 or 1.49. So I'll just choose with the easiest one, 1.5. So over here I'll write this is 1.5, right? In that case, your EMF gets to be 1.5, and you can find out the like gradient at any point. What I would choose, you take two easy points and then find out the gradient using those. For example, this is an easy point because you can clearly understand the y-axis and x-axis coordinates of this very clearly. And again, another easy point would be this one. You can also find out the x-axis and y-axis coordinate of this point clearly. You might draw a triangle across it, or you just take the gradient, like they take these values of these gradient of these 2 points and use the equation separately on your given space. But I would suggest always you take this graph. Okay, so this is the case. Now, okay, so you can find out the gradient. Change in y over here would be 0.6 minus 1.2. So change in y is basically 1.2 minus 0.6, which is 0.6 again. And change in x, wait, sorry. The change in y is 1.2 minus 0.6, which is 0.6, and change in x will be 1.2 and 0.4. You have to subtract 0.4 from 1.2, which is basically 0.8, right? So you can also find out the gradient by dividing the 0.8 over 0.6 over 0.8. So I'll just do the calculation in the given space. For your EMF, find the y-intercept, that was approximately 1.5. You use your graph and obviously, mark it on your graph so that you're obviously using your graph to find out those values. I would also suggest doing all these calculations on your graph. So then again, it proves that you did these calculations on your graph, so use it in the given space again. So now you can find out the gradient, which is basically r is equals to change in y over change in x, which is again 0.6 over 0.8. So if you calculate it, you finally end up getting your values of r as 0.75 ohms, right? Internal resistance obviously will have the same value as ohms, so it will be 0.75 ohms. So just write your answer over here again, 1.5 volt and 0.75 ohms. Moving on to part B, the student placed an identical cell. Remember, this is cell, not a resistor. Okay, so you're placing an identical cell in series with the original cell in the circuit. He connected the voltmeter across the both cells now and repeated this experiment again. The student plotted a new graph of these voltmeter and ammeter readings. Describe how the new graph is different from the graph of one cell. Okay, so if I go back to this original circuit, for one cell you have one internal resistance, but when you have two cell, you get two internal resistance, right? So your gradient, because obviously this graph gives you the value for your internal resistance, right? If from the original graph, if the original circuit has just 1R and the new circuit will have 2R, so the graph will also have twice the gradient, right? I'll just write it down over here again. This is original and this is for the new one. If the internal resistance for the original graph was R and for the new graph it is 2R, so obviously for the new graph it will be twice more steeper than the original graph. And again, if the graph actually gets twice more steeper, it will not actually meet that 1.5 over here, right? It will be higher than that. So if this was the graph for the original one, it is more steeper. I mean, it should be more steeper. So obviously it also gets higher in the y-axis. So if your EMF was just 1.5 for original, it will be 3, right? Twice than that for the new graph. So the statement that you are supposed to write in 12b is that gradient will be doubled and y-intercept is also doubled, right? Or you can just write gradient and y-intercept, both will be doubled. You just need to describe, not explain, so no need to explain the entire answer like I did. Okay, so yes, this is it for the question 12. Then we'll move on to question 13. The diagram shows rays of light traveling from a fish to an observer. The ray of light refracts as the water-air boundary. Now determine the refractive index of the water. You should take measurements from the diagram. Okay, now obviously I cannot take measurements from the diagram because I actually do not have access to a protector in this app that I'm using to write this. So what you're supposed to do, I'll obviously tell you that how to conduct this on your exams, right? How to perform to answer this in your exam. You're supposed to find the angle of incidence and the angle of refraction over here, right? So the light was traveling from the air medium into the water medium, right? So from this medium to this medium. That means this was the first medium, air is the first medium, and water is the second medium. So in the first medium, they are obviously going to create the angle of incidence. And always this angle of incidence, the angle of refraction, and also the angle of reflection, they always are created with respect to the normal, never to the boundary. Okay, so this type of angles will never be calculated, will never be accepted. These are the angles which are actually accepted. This is angle I, this is angle R, angle of refraction. I hope by this time everyone knows how to use a protector. So use a protector and find out the values of I and R. But as I do not have access to protector on my digital devices, so I'll just use the mark scheme. The angle of I was given in the mark scheme as approximately 43 degrees, and the angle of refraction given in the mark scheme was approximately 65 degrees. Now again, if you print this copy again in your home and you start calculating this or measuring this using protector, you will obviously not get these accurate values because Pearson uses quite a different size paper, and we use A4 size paper for our printers right at home. So your values might be slightly different, but overall this is the procedure. Okay, just because of your values are different doesn't mean that your maths is wrong. That is the overall procedure. Now again, this was the first medium and this was the second medium. In the first medium, this was the refractive index of air is always 1, and this was the refractive index of water, which we have to find out. So we'll start writing the equation as N air sine I is equals to N water sine R. Now over here, if you just make NW the subject of this equation, it becomes NA sine I over sine R, which means NA is 1, sine I was 43 degrees, and your sine R was 65 degrees. So if you just use a calculator for this, you're supposed to get the values for your refractive index. So you get your values to be, sorry, I actually made a mistake while reading the mark scheme. This was 43 and this was 65, right? Sorry. The angle of incidence was 65 and this was 43 degrees. Really sorry. So we just have to, like change the values. Over here it will be 65 and over here it will be 43 degrees. Right, so you get approximately 1.328900244. But always remember that the data that they have provided in your question should be less accurate. But they never stated any data. So you can just keep your answer in any decimal place. That's not a problem. I'll choose to keep my answer in 1.33 because that's more convenient. So I'll just write 1.33 as it is a refractive index. So it will certainly not have any degrees or any unit. It's just a ratio. Okay, so with this, our option A ends. I hope it was clear. Moving on to option B. The diagram shows some light from the sun reflecting from the water surface into the eye of the observer. Now, this is the eye of the observer. A light gets like light from that observer. Sorry, the sun is releasing the light. It struck with this air water boundary and is again go back to this observer, right? Because of this reflected light, the observer cannot actually see anything underneath the water surface because light never passed through it, right? Light gets reflected from the water surface. So the reflected light is partially plane polarized. Explain the difference between unpolarized and plane polarized. Now this is a very like repetitive questions, right? For unit 2, this is a must that this might will also appear, like this definition might also appear in your exams because this has been appearing since 2014 maybe in every sessions, in every exams. So just memorize this answer, format answer for your convenience. So if you have to understand in plane polarized light, so let's first start with unpolarized light, right? This was unpolarized light. In unpolarized lights, the vibrations are actually in multiple planes. As you can see, this can represent like vibrations in three planes, right? I can only draw up to three planes, but in real life, unpolarized lights can be vibrating in thousands of planes without any count. But this is your plane polarized light. Now over here for plane polarized lights, they always vibrate in one direction that is also perpendicular to the direction of travel, to the direction of wave travel. So this is the difference between unpolarized and plane polarized. Now you have to express that in words for your option, for your answer in part B1. So let's start that. Unpolarized light has vibrations in many plane as you saw in the diagram, right? In many planes or in many directions should be the correct answer, whereas plane polarized lights in only one plane, that is perpendicular to the direction of the wave travel. Direction of wave travel. Okay, so this is the sample answer for difference between polarized and unpolarized lights. Moving on to part 2, reducing the intensity of the reflected light would help the observer see the fish underneath that sea surface. Explain how the observer can use a polarizing filter to reduce the intensity of the reflected light. Now, if we go back to this diagram again, if for example your reflected light was like like vibrating vertically, in that case you should use a filter with horizontal lines. So what would happen? The filter with horizontal lines will not allow light vibrating in the vertical plane to pass through it. So that means that none of this plane polarized light will be will be entering the observer's eye if the filter is entirely 100%ly blocking that plane polarized light from the sea surface. So if this ray is entirely vanished from here, then obviously the observer can clearly see everything under the sea surface. So what the observer should do, if the light was like, for example, if the light was vibrating vertically, they should use a filter with horizontal filters on it. That means in written statement you should write your answer as if the polarizing, like the observer should position the polarizing field at 90 degrees to the plane of that reflected light. So we write that he should position the filter at 90 degrees to the plane of the reflected light. Right. In that case, no light can enter that filter, so intensity will drop down to zero. To zero intensity. Right. So this is it for your question 13. I hope it was clear enough for everyone to understand. We'll move on to question 14, which was the only star mark question from this paper. So it says the circuit shows, the circuit shown contains a fixed resistor and an LDR connected in series, as we can see, right? So explain why the power dissipated by the whole circuit changes as the intensity of the LDR on the as the intensity of the light incident on the LDR increases. Okay, so your light intensity on the LDR increases. You should refer to the resistance of an LDR changes as the light intensity increases. Okay, in this situation, there's obviously a flow chart for this. As soon as your light intensity across your LDR increases, that causes your resistance of your LDR to decrease, right? So I can just write resistance of LDR to decrease. So whenever your resistance across LDR decrease, the voltage required or voltage across your LDR decreases, which means now over here more voltage will be provided to this fixed resistor, right? So voltage across this fixed resistor, FR represents fixed resistor, that increases. Now again, obviously for your the total voltage, that is still the same, right? Because the power supply is still the same. Total voltage will never change. Now this just the fact that voltage across the voltage shared across that fixed resistor and LDR changes because of their change in resistance. Now another problem appears if you are considering about the resistance, because voltage stays the same but resistance is no longer the same, right? So over here you should use the equation P is equals to V square by R. Now as your this one has a fixed resistor, so the resistance of this fixed resistor cannot change, right? But as your LDR's resistance kind of drops down and they were connected in series, so a decrease in one of the components resisted will cause the total resistance to decrease, right? If I write the equation like this, if RT is equals to R fixed resistor plus R LDR. If this one decreases, this is fixed. In that case, the total resistance would also decrease. And if in that case, if total resistance decreases, as you can see from this equation, I'll just need to write this equation very clearly. P is equals to V square divided by R. If total resistance decreases, in that case, the power dissipation by the circuit should increase, right? But uh, explain why the power dissipation or by the whole circuit changes, right? So yeah, there will be a change, right? That is the overall explanation, that resistance of the LDR decreases, which causes the voltage of the LDR to decrease, but voltage of the fixed resistor increases. But even though the voltage distribution between the LDR and fixed resistor changes, the total voltage supplied by the power supply will still be the same, because we're not changing the power supply, right? Total voltage will still be the same because the power supply is same. But then again, as the LDR and the fixed resistor were connected in series and the resistance of that fixed resistor drops down, obviously in series, whenever any one of the components resistance decreases, the total resistance of that circuit would decrease. In that case, according to this equation, if total resistance decreases as resistance and power are inversely proportional, so obviously your value for your power dissipated by the entire circuit would increase, right? Because they were inversely proportional. So now write the answer. I hope it was clear for everyone. So we'll write that due to increase in light intensity, Due to increase in light intensity, resistance of LDR decreases. So if resistance of LDR decreases due to increase in number of electrons, right? Wait, not that fact actually. You could just write it in this format that as they're connected in series as LDR and fixed resistor are connected in series, then write that equation that RT is equals to R fixed resistor plus R LDR. A decrease in R would cause the total resistance to decrease, right? So if the total resistance of your circuit decreases, then according to P is equals to V square by R, where V is constant because the power supply doesn't change. So due to decrease in resistance, power should increase. Power dissipated by the circuit should increase, right? By circuit, power dissipated by circuit should increase, right? Okay, so this is the answer for question 14. I hope it was clear for everyone. So we'll move on to question 15, right? Okay. Ultrasound can be used to check for cracks in metal beams. The transducer emits a pulse of ultrasound into a metal beam. The same transducer detects the returning pulses. Part of a metal beam is shown. The metal beam contains three cracks, A, B, and C. Okay, this is actually a measurable diagram. That's why they're clearly stating that this diagram is actual in size. The transducer detects a returning pulse from each crack. Explain why there is a returning pulse from each crack. Okay, they are considering that yes, obviously the transducer releases releases pulses, right? But if the at every crack, if they are going to return, right, if they are going to reflect, in that case over here, whatever light passes on, whatever sound passes on, they will be reflected from crack A, and that will be received by the transducer. Then how do you are how you're getting any reflections from crack B or crack C? Because at crack A, any light that was any sound that was actually entered that enters into this metal beam, right, that got reflected from this part, and we are not also releasing any sound from other sides. So that's because whenever at this point, right, at crack A, there's a change in medium. Because of this slight change in medium, some light will be refracted, some light will be reflected, right? So some light gets into this crack B, and over here also some get reflected, and then again some get refracted due to this change in medium. And over here again, some gets reflected and some gets refracted. Finally, over here they will also get another reflection from the overall bottom end of this metal beam. So as they're just looking for the answer for up to crack B, so we'll just keep our answer up to crack B. That some of the pulses at crack A refracts through. So those refracted pulses will reach out to crack B, and then again from crack B's surface, they will be reflected. That will be received by your transducer. So we'll write that some of the pulses refracts through crack A, and those refracted ray will be reflected from crack A. So let's just write also that because there is a change in medium, because they are giving 3 marks, right? So some of the pulses refract through crack A because there is a change in medium, due to the because there's a change in medium of the crack with the metal, right? So because there's a change in medium of the crack with the metal, so eventually those refracted ray will be reflected from that crack B that was received by your transducer. Where they are again reflected. Okay. So this was it, the answer for your question 15A. I hope it was clear. Moving on to the next part. One pulse returns within this time and after being emitted by a transducer. Deduce whether the pulse has returned from crack A, B, or C. You should take measurements from the diagram because the diagram was actually would give you the distance from that top surface to crack A, top surface to crack B, top surface to crack C. If I go back to the diagram again, I'll just erase these diagrams, erase this movement of your lights. This is the distance, average distance from the top surface, from the transducer to crack A. This is again the average distance from the transducer to crack B, and this is again the average distance from your transducer to crack C, right? In this now we have to find out this distance, right? Obviously, as this is an actual diagram, we have to use your scale and find out this distance, which I cannot. So I'll just carry out with that calculation over here. I'll first whenever using pulse echo technique, always remember this is a case for echo, right? That means your sound travels twice the distance. That's why you have to use the equation d is equals to 2 sorry vt over 2, right? So you have the value for your sound, right? The speed of your sound, which is 59,000 across this metal, and the time is also provided to you. So you can use this equation to find out the distance from which this reflected light was actually received. So d would be 59. Obviously writing the equation is a correct method. So you have 5900 multiplied with 1.4 10 to the power of negative 5. So if you divide it by 2, you can finally get the value to be 0.041 meter. If you convert this to centimeters by multiplying it with 100, you get approximately 4.1 centimeter. So now again, if you go back to your diagram, you measure the 3 distances. It happens to be the distance for your part 1, okay, or the distance to be your for crack A. This was the distance, which is approximately 4.1 centimeters. So in that case, you can just write that it was from crack A. Obviously, I use the mark scheme. That's why I know for crack A, the distance was 4.1. You are supposed to do that measurement with the diagram and then, match the values. Whatever value was closest to this 4.1 centimeter, you just choose that crack. Okay, so now moving on to part C, explain why ultrasound used to detect cracks in metal beams usually have frequencies of megahertz, not with kilohertz. Megahertz means hertz to the power of 10 to the power 6, right? Hertz multiplied to 10 to the power of 6. So in that case, for megahertz, that means it has a higher frequency, right? Velocity, to be honest, across this metal doesn't change that much. So V is equals to F lambda. If you convert this to F is equals to V multiplied with 1 lambda, where V is constant because across the entire metal velocity is same. If you're using higher frequency, that means there will be smaller wavelength. If the wavelength is very small, then there's less chance that any gap will be sufficient enough, like will be equal to your wavelength. And if your gap is not equal to your wavelength, if your gap is like very large compared to your wavelength, in that case diffraction will not occur, or even if diffraction is occurring, it will be a very smaller extent. For smaller diffraction, your resolution will be more perfect. You will have a higher resolution. You will get a more detailed possible uh, reflected dry light or some things, right? So that's why using higher frequency is important, because that gives you lower wavelength and therefore greater possibilities of greater details, of achieving greater details is possible. So we'll write that at higher frequency, wavelengths are smaller. So we'll write wavelengths are smaller, therefore less chances of diffraction and a greater level of detailed uh, reflected waves, and achieving a greater level of detailed reflected waves are possible. I'm sorry, I forgot the spelling for achieving, so I'll just write of gaining. Okay, less chances of diffraction and gaining greater level of detail reflected are possible. Okay, so this was for question 15C. I hope it was clear for everyone. We'll move on to 16. So for question 16. So for question 16, it says that drivers use car headlights to emit light in dark conditions. The graph shows how current I varies with potential difference V for a current headlight. The headlight will emit a light when it dissipates at least 35 watt of power. Determine the minimum potential difference for this for which the headlight will emit light. Okay. Determine the minimum potential difference for which the headlight will emit light. Okay, so what you have to do is that you have to choose any of the voltages from this diagram that will give you the value for your this 35 power. You have to obviously use the equation V is equals to IV, P is equals to IV, and you have to take random numbers from your graph and find out that at what value your value for your 35 is restored. So as you can see that your voltage values span from 0 to 12. If you take maybe like 5, right, the 5 over here only reaches up to almost 2.7. So 5 multiplied with 2.7 only gives you 2.7 only gives you 13.5. That would not be the possible answer. Then again you can take 6, which only spans up to 3 point almost 2, right? So 6 multiplied with 3.2, you get again 19.2, which is not even sufficient. You move on to 7. 7 gives you 3.4. So 7 multiplied with 3.4 current which is again 23.8, not close to 35. You can move on to 8, which is almost close to 3.7. So you can write again 8 multiplied with 3.7, which is again 29.6, but not 35. You move on to 9. 9 is approximately close to 3.9 over here, right? As you can see. So you multiply 9 with 3.9, you get 35.51, which is certainly close to your value for 35 watt. So you can write that you have to prove it obviously. You obviously take these diagrams like points from the graph. Okay, now over here you just write I is equals to P is equals to IV, which is 3.9 multiplied with 9, and that gives you 35.1 watt. So the minimum voltage required for these headlights to be on is 9 voltage, right? So you can just write over here that's 9 voltage. Okay, so this was it for question 16A. Moving on to question 16B. In a car, two headlights are connected in parallel with a 12-volt battery. The battery has a negligible internal resistance, so small r is 0 over here. And explain the advantages of connecting the headlights in parallel with the battery rather than in series. It's quite common. We have already learned this kind of questions from our IGCSEs, right? That in parallel we can control the headlights individually, and again if one headlight breaks or fails, it doesn't mean the other will also fail. It will remain to work, and then again in parallel headlights, each one will receive 12 volt, but in series each one would have received 6 volts, right? So in parallel headlights they will be twice as brighter than they were in series connection. So yeah, these are enough for the 3 marks that they have provided. So I'll just write that in parallel, if one headlight breaks, the other will continue to work. Also, each headlight now receives 12 voltage. So now they will be more brighter, right? More brightness. Okay. So this was it for B1. Moving on to B2, a student writes the following statement. When connected to the 12-volt battery, the combined resistance of the two headlight in parallel is 1/4 of the combined resistance of the two headlights in series, which means they're indicating that RP, resistance in parallel, is actually uh, yeah, 1/4 of RS, right? Whatever the value for RS is, that will be 1/4 of your total resistance in parallel combination. If I'm not wrong, yeah, that is it, the case. Okay, so deduce whether the student is correct or not. For example, if I have to use like numbers, if RS is like 16, in that case, RP, that would be not exactly 16. 16 is quite confusing. Let's just use right. If this is like 32, if this is like 32 ohms, and in that case, the total resistance of parallel combination would be just 8 ohms, which is like, 1/4 for that resistance in series connection. So again, you have to use your graph and find out the values if this statement is correct or not. So from your graph, this was actually the graph where you can use both the parts. For example, in parallel, each bulb would be receiving 12-volt voltage, right? In that case, the current for them would be 4.6, and in series each bulb would be receiving a 6-volt voltage, In that case, they're approximately receiving 3.2, right? 3.2 ampere of current. So from this current, you can actually find out the resistance of each resistor in series and in parallel, and then find out their combinations separately, and then find out their ratios also. So if you have to find out for parallel combination at first, from graph we calculated that for parallel combination, each resistance was receiving 12 volt, right? So we can write that each resistor receives 12 volt. In that case, each resistor receives 12 volt. In that case, we can write V is equals to, sorry, not V is equals to, from the graph we found out the current to be 2.4.6, right? So from the graph we got the current to be 4.6, and we can find out the resistance according to the equation V over I, which is 12 over 4.6, and that is almost 2.61 ohm. Now this was just the resistance for one resistor. If we find out the resistance for the total combination, we know that this is the situation for reciprocals, so that will be 1 over 2.61 plus 1 over 2.61. So if you do the calculation, 1 over 2.61, so you get your value as 0. 200 over 2.61. So just invert it and you get 261 over 200. That is 1.305. Okay. So for RP, you actually get 1.305 ohms. Okay. Now again, you do the calculation for series. For series again, the each resistor receives now 6 volt. Which is basically from the graph we saw current would be now at this point 3.2 amps, right? From the graph we calculated. So R would be now V over I, that's 6 over 3.2, which is almost 1.875 ohm. And eventually for R series, you just add this value 1.875. So you get 3.75. Okay. So again for series combination, you get 3.7, almost 75 ohms. Eventually, if you want to find out the ratio, you can see that if it is exactly a 1 by 4 or not. So if the ratio over here would be, you get it to be almost of 2.87, right? This is not nothing close to your 4 times, right? So if this is the case, then not, the student was not correct, right? The parallel combination is not 1/4 of the series combination, so you can just write not correct as a final statement for this. So yeah, this was your calculation for 16 part B3. I hope it was clear for everyone. We'll move on to part C. The headlights are connected in the circuit using copper wire. The current in the wire is almost 4.6. Calculate the drift velocity of the electrons in the copper wire. They have given you some information, that resistance per unit length, resistivity, and your value for number of charge carriers. Okay, so they have provided with you resistivity, resistance per unit length, right? Okay, for that drift velocity, we're obviously using the equation I is equals to NA VE, right? Where V is unknown, drift velocity, area is also unknown. For that area, they have provided you with resistance and resistivity per unit length. So in this case, you have to use the equation of that resistivity also, which was like resistance was equals to resistivity length over area. As over here you're using actually over here you're actually using I think a length of 1 meter maybe, if I'm not wrong. Right, this is for 1 meter, so that's correct. We just have to make A the subject, which is resistivity length over resistance. Resistivity is given to you as 1.7 2 into 10 to the power of minus 8, and resistance per unit length is given to you as 1.75 multiplied with 10 to the power minus 2. If you calculate this, you get the value for your area to be 9.83 into 10 to the power negative 7 meters square. So now you have the value for area and everything that you need. So you can now calculate your drift velocity. If you just make V the subject of this. Okay, so now with this value for your area, you can calculate the value of your drift velocity. From this equation. If you rearrange, it becomes I over charge carriers current multiplied with electrons, like charge of electrons. So we can now write so V is equals to I over NAE, which is basically 4.6 multiplied with charge carriers is 8.49 multiplied with 10 to the power of 28. That gets multiplied with the area, which is 9.83 multiplied with 10 to the power of negative 7. And eventually they get multiplied with your number of charge carriers, or the charge of electrons, right? Which is 1.6 multiplied with 10 to the power of negative 19. So if we calculate all these together, again, remember to use, like the brackets over here very explicitly. So if you calculate it, you get 3.4 multiplied with 10 to the power of negative 4 meters per second. So this is the value of your drift velocity. So this was it for end of your question 16. So we'll move on to question 17. The diagram shows the energy levels for an atom of hydrogen. You have this is N0. This is 1, 2, 3, 4, 5. Energy levels up to shell 5, and an electron is in the 13.6 electrovolt ground state level of the atom. A photon interacts with this electron. Explain why this interaction causes another photon to be released. Okay, now that's because whenever there's an electron over here, right? A photon with a discrete packet of energy, right, travels, and that is absorbed by this electron. So after receiving the discrete packet of energy, they will obviously rise up to a higher energy level, any position along this diagram, right, along this level. So I'm assuming that they will move on from this ground state to that higher energy level to level 1. Now they can certainly not always be over here, because this was not their original state. So what happens, they move on to their they move down to their ground state, and over here from this part, they actually release an electron, right? Like, so sorry, they not release an electron. Like when they move on to their ground state, they release that photon particle, and that's when you actually see the light spectrum of that, gaseous part. So yeah, um, this was the actual explanation, that they receive energy, move on to a higher energy level, and then when they fall back to their ground state, they release that energy again in the form of photon. So the answer over here should be that electrons moves to like after receiving a photon particle, or after receiving a discrete packet of energy, electrons move on to a higher energy level, and they then again drop back to their ground state, releasing another photon particle. So we'll write that after receiving a photon, electrons move up to a high energy level. After receiving a photon, electrons move up to a higher energy level. Um, and then again drop down to their ground state, releasing a photon or releasing another photon. So with this, their question 17A ends. I hope it was clear. Moving on to 17B. 17B, a photon has a wavelength of 280 nanometers. So obviously we have to convert this into meter, where it will be 218 multiplied with 10 to the power of negative 9 meters, right? This is the value of your wavelength then. And we have to determine the energy in electrovolt of this photon. Okay, so in order to find out the energy, we have to use the equation, wait. Yeah, since we are using a photon always has a speed of light, right? Which is 3 into 10 to the power of 8 meters per second, right? So you can first find out the frequency, and using the frequency and Planck's constant, we can find out the energy, right? So we just have to find out the frequency first. That will be velocity over lambda. That's 3 into 10 to the power of 8. This entire thing divided by 218 multiplied with 10 to the power of negative 9. Right, if you just multiply it, you get approximately 1.38 multiplied with 10 to the power of 10 to the power of 15, right? Yeah, this hertz. This is the value of your frequency. Now using the Planck's constant and this equation, you can find out the energy, which is 6.63 multiplied with 10 to the power of negative 34, again multiplied with 1.38 into 10 to the power of 15. So if you calculate this, you can find out the energy, which is almost 9.12 10 to the power of negative 19 joules. Okay, now you got the value for your energy, but the problem is it is in joules, right? But they specifically want it in electrovolts, so you have to convert this into electrovolt. That is by just dividing it with 1.6 into 10 to the power of negative 19, right? So I'll just write it in this part. That is, you just divided it with 1.6 into 10 to the power of negative 19. So when you calculate this, you approximately get 1.70 electrovolt. So this is how you're supposed to do your working in order to find out the energy in terms of electrovolt. So we'll now move on to 17b2. Explain whether the atom of an hydrogen could emit a photon with this energy. So in order to find that, you have an energy of 5.70 electrovolt, right? You try to find out the, energy difference between these every level. For example, I'll erase everything over here. Okay, so if I have to find out the value for this, what would I do is that minus 13.6 minus 3.4, right? So you just do this entirely like this I did in the screen, right? With brackets and everything. 13.6 minus 3.4. So you get it to be almost 10.2 EV, right? Then again for this part, if the same working, wait, sorry, I actually made a mistake. It should be actually 3.40 minus 13.6, right? Then you'd get the value to be positive electrovolt. And then again, the similar working, minus 1.51 minus 3.4, which is again minus 1. Yeah, right, that's fine. 51 minus 3.4, which is almost 1.89 electrovolt. Nothing is close to your 5.7, right? So you continue doing that. Minus 0.85 minus 1.51, sorry, minus 0.89 minus 1.51, which is approximately 0.52, so 0.62. Again for this one, minus 0.54 minus 0.85, again that's almost 8 point something. So if you continue to do this for every possible combination, you'd see that nothing gives you, or nothing is any way closer to 5.7 electrovolt. So you have to write it down over here that at any point the differences between the energy levels are not like specific to 5.7. And even if it's like very close to 5.7 but not exactly the same, there will be no photon emission, right? Because over here electron differences carry energy which has to be very discrete, right? If it is not discrete, then the electrons will not be excited to a high energy level. So you just write that electrons, sorry, the differences between the energy levels are very discrete. So, and there are like no differences on the electron, sorry, energy levels with zero point 0.5 electrovolts. So there will be no possible electron, like photon emission for this specific amount of energy. So you can write that differences between energy levels are discrete. So are discrete, and as there is no difference between energy level with 5.4, 5.7 electrovolt, as there is no energy level, as there is no energy level with difference of, as there is no energy level with difference of 5.7 electrovolt, so there are no possible electron emission for this energy. No photon emission for this. Right. So with this, our entire 17b2 ends. I hope it was clear. Moving on to 17 C1. The photons with energy 1.63 into 10 to the power of negative 18 joules are incident upon the surface of a metal plate. The metal plate releases electrons due to the photoelectric effect. The maximum possible speed of the electrons have to be calculated. They have also given you the value for work function to be 5.89 10 to the power of negative 19 joules. Okay, so you can calculate it using the equation of E is equals to work function plus kinetic energy, right? So now the value for E is already provided to you, 1.6 into 10 to the power negative 19. The photon energies gives you the total energy. So you just take kinetic energy, the subject, E should be broken down into HF, or not HF, sorry, you have already been provided with the value, right? So no need to work anything. You can just subtract the values of 5.89 from this 1.63. So that will be 1.63 multiplied with 10 to the power of negative 19, and subtract 5.89 multiplied with of 10 to the power of negative 19 with this. So half, again, your value for your kinetic energy should be broken down into half mv square. So that's half mv square, and the final result for this subtraction should be equal to 1.04 multiplied with 10 to the power of negative 18. So if you just make v the subject, it becomes 1.04 multiplied with 10 to the power of negative 18. This entire thing multiplies with 2, and finally this will be divided with the mass of your electron, which was 9.11 10 to the power of negative 31. An entire thing will be under a root because you had a velocity square on the equation. If you calculate this, you approximately get a value of 1.5 10 to the power of 6 meters per second, right? Which is almost the value of your velocity. So yeah, this is it. I hope part C1 was clear. Moving on to part C2, explain why the photoelectric effect demonstrates light behaving as a particle, not rather than as a wave. Because over here, every energy of the photon increases due to increase in frequency. The intensity of this light does not actually depend affect the release or your or your electron emissions. Again, photon energy must be greater than their work function for that kinetic energy to be possessed. That is also very discrete values, which are only acceptable for particle behavior, not for wave. If it was a wave, then even if there's a 0.1 and 1 amount of 1 joule of energy provided, there will be electron emission, because for every small amount of energy there is vibrations, right? So for wave theory, every energy would cause electron emission. For particle theory, discrete values of energy will cause electron emissions, right? So that's why they represent particle theory, not the wave theory. Lastly, each photon only interacts with one electron. It's not like that if there is a group of electrons at this shell and one photon enters that shell, every electron will receive it and share the energy. That is not the case. Only one electron at a time can receive that photon energy. So all these things actually indicate to the particle behavior, not to the wave behavior. So we'll just write the answer that the energy of a photon increases as frequency increases. Also, photon energy has to be greater than the work function, and only one electron can interact with each photon for to move up to a high energy level, right? Again, only one electron can interact to only one electron can interact to a photon to move up to a higher energy level. Okay, so this is it for question number 17. We'll move on to question 18. The photograph shows a musical instrument called a violin. The violin has four strings. Each string is held at a fixed position by a peg and at a bridge. When a string is plucked, a stationary wave forms on the string. Explain how a stationary wave forms onto the string. Now, stationary waves are the one that are only reflected, at every at the every end of these strings when they are connected at the pegs, right? And when again those strings are reflected, they actually superpose with the original wave, eventually causing interference to occur. So these are the concepts of here stationary waves to be formed. So we can write that waves on a string are reflected at each peg, and because of this they superpose with the original waves, causing nodes and antinodes, right? And antinodes. Yeah, so this is it for question 18b. We'll move on to question 18c. The simplest stationary wave that can be formed on the string as a node at each end and an antinode at the center as shown. The frequency of the wave is called fundamental frequency. The strings on a violin have different fundamental frequencies as shown, and the tension in one of the strings is this much, and the length of the string is 32 centimeters, which is almost 0.32 meters, and the mass per unit length of the string is 2.03 into 10 to the power of negative 3. So we need to deduce whether this string is actually string 1, string 2, string 3, or string 4. In order to find that, we have to find out that value for your frequency, right? So at first, for frequency, we have the wavelength over here, right? For one complete wave, the wavelength would be 0.32. And as you can see, this is half of the wavelength, right? This is not one complete wave, this is half of the wavelength. So you can write length is equals to um, lambda over 2, which can be further broken to lambda is equals to twice L. So in this case, you have to first find out the value for your velocity. Using that velocity and lambda, you can find out your frequency. And whenever your frequency matches with any of the fundamental frequencies of each string, that string is actually being used in this situation. Right, so over here, at first, we have to find out the velocity. We have to find out the velocity using this tension and mass per unit length. We have the equation, which is velocity is equals to tension over mass per unit length under a root, which is basically 71.5 over mass per unit length was 0. Like 2.03 multiplied with 10 to the power of negative 3, everything under a root. So if you calculate it, you get 187.7 meters per second. Right, so this was your value for velocity. Now using this, you can find out the value for your frequency, which is 187.7 divided by twice lambda. Lambda was 0.32. So if you again calculate it, you get 293 hertz, which is approximately the second string, right? So you can just write this is string 2. And that will gain you the 4 marks over here. So we'll move on to this 18C over here. The stationary wave on the string causes sound waves to be transmitted through the air. Describe the similarities and differences between stationary waves on the string and the sound waves transmitted through the air. Okay, weirdly they are providing 5 marks over it. Obviously, the stationary waves that are being created on the strings are transverse and the sound waves are obviously longitudinal, right? So for longitudinal waves have like what? Um, Longitudinal waves for amplitude will be same for every point. For transverse wave, amplitude is not same for every point, right? And then again, I mean, if it's like transverse in sound, so in your standing wave, right? Then in that case, they're not transferring energy, but in sound, in air, they are transferring energy. Right? So these are the differences. For similarities, you can see that. In this situation, waves, both the waves, stationary and standing, standing and that like longitudinal waves in air, they both have the same frequency. Obviously, they will both have the same speed over here, right? Same wavelength over here. So other physical properties are quite similar. Other than the other than being that they are both different in form of wave. Sound is transverse, whereas stationary is longitudinal. Sorry, stationary is longitudinal and sound is transverse. So we'll just write the answers that um, stationary wave, stationary wave is transverse, whereas sound waves are longitudinal. Stationary waves, we can say that stationary wave um, transfers energy, so it doesn't transfer energy. Stationary wave doesn't transfer energy, but longitudinal wave would transfer energy. And then again, stationary wave um, have same Sound wave has same amplitude for all points, but stationary wave doesn't. Doesn't. Lastly, the similarities. Both waves have same frequency, speed, and wavelengths. So yeah, this is it. Thank you for watching this entire video. This was the end for your May 23 Unit 2 question paper. Thank you for watching.